Welcome to the definitive edition of the Geospatial AI Revolution. We've consolidated our four-part series, from market surges and data pipelines to AI-driven automation, into one complete masterclass.
We begin with part 1, why AI-powered satellites are Wall Street's new favorite SaaS. Let's dive in.
For years, investing in space technology felt like a gamble. You were backing capital-intensive, cash-burning hardware projects where success was measured mostly by counting how many rockets actually made it off the launch pad. This chart shows the dramatic decoupling that occurred in early 2026. Notice how the broader, volatile space tech index stays relatively flat, while the Earth observation sector breaks away on a massive upward trajectory. Planet Labs alone saw a 658% surge over 12 months. The market stopped treating these companies like aerospace manufacturers and started valuing them on enterprise software metrics, specifically annual recurring revenue and remaining performance obligations. The numbers climbed because the business model changed. Historically, buying satellite data meant paying opaque per square kilometer rates with massive minimum orders. By 2026, providers replaced that friction with API-driven Insights-as-a-Service subscriptions. Customers no longer buy a heavy image file. They subscribe to a lightweight, automated alert telling them exactly what changed on the ground. But these identical-sounding software metrics mask a much deeper reality. A subscription to one company might rely on an array of 5-kilogram cameras, while another depends on a multi-ton radar dish. You cannot just look at a balance sheet to understand who wins this market. You have to evaluate the strict physical laws governing the sensors actually orbiting the Earth. There is no master satellite that does it all. The laws of orbital physics and optics force every operator to make strict compromises. This trade-off triangle illustrates the three defining constraints of the industry. At one point, you have spatial resolution, how clear the image is. At the second, temporal resolution, how often the satellite revisits the target. And at the third, phenomenology, whether the sensor uses optical cameras, radar, or radio frequencies. You cannot maximize all three at the same time. When you choose a provider, you are betting on which specific corner of this triangle is most critical to the end user, and which capability will command the largest share of enterprise and defense spending. Filtering the hype through these physical limitations is the only objective way to figure out who has a defensible commercial moat and whose hardware is obsolete. The most common form of Earth observation is passive optical imagery. It relies entirely on reflected sunlight to capture the visible surface below. Planet Labs attacked this market by scaling down. They deployed an active fleet of over 200 Dove nanosatellites, using commercially available parts to keep manufacturing costs incredibly low. Each 5-kilogram unit means you can pack dozens onto a single launch vehicle, drastically reducing the friction and cost of reaching orbit. The resulting trade-off heavily favors revisit rates. Planet captures the entire global landmass daily, but only at a 3-meter spatial resolution. That is perfect for tracking macroeconomic trends, like deforestation or urban sprawl, but lacks the clarity required for precise military targeting. Vantor operates on the exact opposite end of the spectrum, with its Worldview Legion constellation. These are 630-kilogram machines, designed for maximum fidelity. A Vantor satellite delivers imagery at a 30-centimeter resolution, backed by an 8-band spectral analysis capable of assessing minute details, like the health of specific crops or precise coastal depths. But that hardware requires hundreds of millions of dollars in capital expenditure to build and launch. Because of their size and cost, Vantor has fewer assets in orbit and must prioritize specific, high-value targets over persistent global monitoring. Positioned firmly in the middle is BlackSky. They utilize mid-inclination orbits and connect their constellation via optical inter-satellite links. This architecture doesn't rely on flying directly over a physical ground dish to send data back to Earth. As a result, BlackSky can capture, process, and deliver insights in under 90 minutes, revisiting heavily populated geopolitical targets up to 15 times a day. The optical market is highly stratified. You have Planet for broad economic monitoring, Vantor for deep, high-resolution analysis, and BlackSky for rapid response situational awareness. Regardless of resolution or revisit rates, all optical sensors share a fatal weakness. If a target is covered by darkness, dense clouds, or thick battlefield smoke, an optical camera sees nothing. Synthetic aperture radar, or SAR, bypasses the atmosphere completely. Instead of waiting for sunlight, a SAR satellite actively fires microwave pulses toward the ground and measures the backscattered signal, effectively mapping the terrain below through any weather condition, day or night. The Finnish company ICEYE currently dominates the commercial scaling of this technology, operating the largest SAR constellation in the world. American operators like Umbra and Capella Space boast highly competitive radar systems, but they operate under strict international traffic in arms regulations, or ITAR, which severely limit the data they can export. These export limits lock American firms out of international deals, handing ICEYE a massive structural advantage to capture global market share without U.S. regulatory friction. This regulatory freedom translated directly into massive sovereign commitments, like ICEYE's €1.7 billion contract to deliver a dedicated radar constellation for the German military. Because national security cannot pause for bad weather, SAR's 24/7 persistence has made it the primary destination for defense procurement, providing an unshakable capital anchor for operators who can deliver it. Imagery, whether optical or radar, only captures the physical surface. The next layer of intelligence collection ignores the visual spectrum entirely. Spire Global operates over 100 satellites that carry 0 cameras. They intercept maritime and aviation radio frequencies and measure how GPS signals refract through the atmosphere. By feeding that raw atmospheric data into NVIDIA's digital twin architecture, Spire generates proprietary AI weather models that predict highly detailed operational forecasts up to 20 days out. Machine learning capabilities have migrated from terrestrial data centers to the orbital edge, beginning with Planet Labs' Pelican constellation. By installing advanced compute modules directly on the spacecraft, the Pelican 4 satellite executes machine learning inference in orbit. It identifies target assets and delivers finished intelligence before the data ever leaves the vacuum of space. Instead of waiting to downlink a massive multi-gigabyte image file, the satellite instantly identifies the target and beams down a tiny text alert over a low-bandwidth connection. It slashes the time between an event occurring on Earth and the user receiving the intelligence. Putting compute on the edge turns a satellite from a passive recording device into an active, thinking node in a real-time global intelligence network. The operators best positioned to survive the next decade are the ones who lock in massive multi-year intelligence contracts and then use that baseline capital to fund high-margin, frictionless commercial software. Here is the structural framework for evaluating these providers in 2026. Every operator solves a distinct problem. If an organization requires absolute 24-hour persistence, regardless of weather or cloud cover, the capital flows to ICEYE and the synthetic aperture radar operators. If the goal is broad economic monitoring, mapping global supply chains or daily agricultural yields without the friction of bespoke imaging orders, the scale tips to Planet Labs' high-frequency coverage. And for users demanding extremely low latency, the ability to task a sensor and receive intelligence on a specific target within 90 minutes, BlackSky commands the advantage. Understanding exactly what the end user needs to accomplish is the only reliable way to value the hardware floating in low Earth orbit. But before allocating capital based on impressive software margins, you must account for the systemic, physical risks woven into the space economy. The entire sector suffers from an extreme infrastructure bottleneck. If an anomaly forces a prolonged grounding of SpaceX's Falcon 9 fleet, constellation deployments grind to a halt. When satellites stay on the ground, revenue recognition timelines are immediately severed. Beyond the launch pad, there is a massive liquidity risk looming in mid-2026, the anticipated $1.5 trillion initial public offering of SpaceX itself. An offering of that magnitude has its own gravitational pull. It threatens to act as a liquidity vacuum, instantly siphoning institutional capital away from the smaller, specialized Earth observation providers we've discussed. Ultimately, generic excitement about the space economy will not protect a portfolio. The true value in geospatial intelligence rests on 3 very specific pillars: the ease of the data API, the strict physics of the orbital sensors, and the absolute certainty of multi-year sovereign defense contracts.
In Part 2, we move into the technical core, building a geospatial AI pipeline to track the global economy from space.
In the days leading up to a quarterly earnings report, the most valuable data in the world is physical. If an investor can track the volume of freight moving in and out of a competitor's distribution center, they can build an independent revenue forecast before the market reacts. Building that forecast requires monitoring the velocity of heavy transport logistics moving along dedicated industrial corridors. But there is a physical limitation to consider. At a resolution of 10 meters, a 20-meter truck disappears entirely into two solid, low-resolution pixel blocks. At this scale, you cannot count the vehicles. Instead, the target is a specific blue, green, and red spectral smear spanning 3 to 5 pixels across the highway. This anomaly occurs because the Sentinel-2 satellite does not capture all colors simultaneously. It records red, green, and blue light roughly 1.01 seconds apart. For an object moving at highway speeds, that interval creates a physical separation of the color bands in the final image. Exploiting this temporal offset once required massive institutional capital. Today, an independent actor can execute the exact same mathematical extraction for less than $100. The barrier to entry for planetary intelligence has moved from the size of a capital budget to the precision of a technical workflow. Historically, the procurement of satellite imagery was a manual, restrictive process. Enterprise licensing and massive minimum order areas meant that small firms were priced out of the market entirely. Market reforms in 2026 have replaced that bottleneck with transparent, API-first marketplaces. Platforms like UP42 and SkyEye allow users to define exact bounding boxes and pay only for the data they need. This shift has collapsed minimum order sizes. Where sovereign militaries once bought thousands of square kilometers, an individual can now purchase as little as 1 to 5 square kilometers. The cost of this data is now governed by 3 clear variables: the spatial resolution, the age of the archive, and the total order area. As this matrix shows, an investor on a $100 budget can now secure 5 square kilometers of archive data at a 30-centimeter resolution. This modular pricing provides the same spatial access to a solo researcher that was previously reserved for large institutions, allowing for low-cost experimentation. Purchasing the imagery is only the first step. The real challenge is processing the complex multispectral data arriving from orbit. There is a common assumption that a user can simply feed a raw GeoTIFF file to a large language model and ask it to count objects. In practice, direct visual classification by AI models has a 0% success rate when identifying subpixel objects in low-resolution imagery. The model cannot identify details that the sensor's physical resolution didn't capture. Advanced agents like Claude 4.6 Sonnet are not utilized as visual classifiers. Instead, they act as orchestrators for the underlying spatial mathematics. These agents bridge the gap by taking a natural language directive and writing the complex Python scripts needed to parse Earth observation data. Modern GEOINT is a deterministic mathematical problem. It is not a matter of image recognition. Google's Gemini 3.1 Pro is designed for this type of complex reasoning. Its 1 million token input window allows it to synthesize entire codebases without truncating the logic. The model integrates with Google Cloud to ingest AlphaEarth embeddings, 64-dimensional vectors that distill petabytes of planetary data into analysis-ready formats. To manipulate this data, the AI writes its scripts using a set of standardized Python libraries. Rasterio is the foundation for reading and writing raster data, allowing the script to extract raw spectral bands from the satellite image. GeoPandas manages vector data, calculating the exact spatial overlap between a property boundary and the satellite pixels. X-Ray manages multidimensional data cubes, making it possible to track historical trends and seasonal anomalies across months of imagery. By commanding these 3 libraries, a single user effectively operates an automated, virtual GIS department. Raw satellite data is messy. It arrives distorted by atmospheric light scattering, water vapor, and aerosols. The first task is writing a script that converts top-of-atmosphere radiance into mathematically accurate surface reflectance. The script then applies a cloud masking algorithm, which identifies and nullifies pixels containing thin clouds or shadows that would otherwise skew statistics. All data is then reprojected into a unified coordinate reference system to ensure precise alignment with ground-level maps. Once the data is clean, the AI generates a random forest classification script. This isolates the specific color variants along a highway corridor. The code validates the presence of the separated red, green, and blue bands, confirming the object is moving at speed. By measuring the spatial distance between these bands across the 1.01-second delay, the script calculates the vehicle's exact speed and heading. This rigorous pre-processing is what allowed as an investor to turn optical noise into an independently verifiable economic indicator. Deploying generative AI for financial analysis involves a major risk: data hallucination. If an agent fabricates a geographical statistic or an object count, the resulting forecast is worthless. To prevent this, the workflow uses automated reasoning checks. The AI is restricted to generating deterministic Python code, ensuring that all results are calculated by logic rather than probabilistic text generation. Next, we use multi-sensor cross-validation. Findings from optical imagery correlate against structural density data from radar sensors, confirming a visual anomaly has physical mass. Finally, vetted document fencing restricts the AI's context strictly to verified supplier metadata, preventing it from filling data gaps with assumptions. This multi-layered verification is the only way to guarantee analytical integrity in a high-stakes environment. This architecture scales across sectors. It allows a small agricultural firm to predict crop yields by calculating vegetation vigor weeks before the harvest. It translates to monitoring maritime logistics and container throughput at global shipping hubs. The institutional monopoly over physical world intelligence has ended. An individual with a Python script can now observe industrial throughput once reserved for sovereign intelligence agencies. The competitive advantage has moved to those who can bridge remote sensing data with automated AI orchestration. The capacity to independently verify global economic activity from orbit provides a primary source of truth that exists outside of company press releases or official government statistics.
Next, in Part 3, we examine the democratization of space and why satellite data is now a utility for the retail market.
In 2026, the Earth observation market reached a $117 billion valuation. The sector has transitioned from experimental research into a cash-generating industry. Historically, accessing this technology was a slow, expensive process. It required heavy capital, strict non-disclosure agreements, and weeks of waiting for price quotes, locking out everyone except defense agencies and global conglomerates. Today, satellite imagery functions as a retail utility. Multi-orbit architectures and AI have reduced the barrier to entry to a browser-based transaction, where users can purchase specific data for as little as $25. Companies like Planet Labs demonstrate this transition. By achieving their first full year of profitability with record revenues, they've shown that the commercial space sector is now built for high-volume, mass-market use. This data gives individual homeowners and small businesses access to the same evidence once reserved for the elite, providing a clear record for insurance claims and competitive analysis. This level of access creates a new problem: paralyzing choice. Today, there are over 700 distinct commercial sensors in orbit, each with different payment structures and technical capabilities. You don't need a geography degree to use these tools, but you do need procurement discipline. Without it, you risk spending your budget on imagery that is the wrong scale or resolution for your project. This chart shows the primary trade-off. You must balance your need for high-resolution detail and frequent updates against your budget and order size. To navigate this, identify your group: the macro baseline user, the sporadic retail user, or the continuous monitor. Success in this market comes from matching your specific situation to the right economic platform. The baseline for global monitoring is the collection of free, publicly funded programs like Landsat and the Copernicus Sentinel missions. These platforms provide massive regional coverage and decades of historical data. For tracking long-term environmental shifts or regional land use, the cost is zero. Gateway platforms like EOS Land Viewer make this data accessible through a browser, allowing beginners to search and filter these public catalogs without specialized software. The limitation is the detail. These satellites pass over a location every 5 to 16 days and offer a median resolution of 10 to 30 meters per pixel. While excellent for mapping forests, 30-meter resolution makes individual houses blur into city blocks. For property-level detail, you have to move up. When you need structural details, like a homeowner proving their roof's condition to an insurance company, the commercial sector is the only viable option. Marketplaces like Skywatch and UP42 have simplified this using standardized licenses and credit systems, allowing small businesses to make micro-purchases without negotiating enterprise contracts. Paying for data provides a significant increase in clarity. You move from 30-meter blurs down to commercial resolutions of 15 to 50 centimeters, where you can identify individual tree canopies and equipment defects. The entry price is low. You can access historical archives for as little as $25, or request a new satellite capture for areas as small as 1 square kilometer. However, optical satellites cannot see through clouds. To avoid wasting capital, use the platform's preview tool to ensure your target is clear before you pay. If you need to see through cloud cover or monitor a site at night, you have to use synthetic aperture radar. Because this requires specialized sensors, it carries a higher starting price, often around $450. Pay-as-you-go marketplaces offer powerful visual evidence for single events, as long as you meticulously verify the image quality before the final purchase. For operations that change daily, like an agricultural cooperative monitoring crop growth, single one-off images aren't enough. Users rely on the hectares under management model from providers like Planet Labs and Sentinel Hub. You pay a larger upfront annual fee, such as $9,650, but in return, you get automated daily monitoring over your specific area of interest. Processing this volume of data has also been simplified. Instead of heavy desktop software, you can drop imagery files directly into browser-based platforms. These tools use the Normalized Difference Vegetation Index. By calculating the ratio of near-infrared to red light, the software reveals invisible crop health. The result is a color-coded map highlighting stressed crops, allowing farmers to apply water or fertilizer only where needed. For high-frequency needs, this subscription model changes the value. You aren't just buying images. You are acquiring a continuous stream of operational data. To find your best option, follow this decision framework based on what you are trying to accomplish. If you are an NGO or researcher tracking large-scale environmental changes, start with the free Copernicus and Landsat data on EOS Land Viewer. For homeowners needing evidence for an insurance claim or property dispute, use high-resolution archival data on Skywatch or SkyFi to get the detail you need at a low cost. For civil engineers monitoring a specific construction site, use UP42. Its credit system and low minimum area requirements are designed for localized commercial projects. And for agriculture or supply chain monitoring, use the Sentinel Hub and Planet subscription models to get near-daily updates for a fixed annual price. Success in this market depends on matching the platform to your specific budget and site frequency needs. Emerging technology moves processing into space. Next-generation satellites will run object detection algorithms in orbit, sending lightweight alerts rather than raw, heavy image files. Digital marketplaces have replaced slow, exclusive procurement systems, providing transparent access to spatial records. Today, throughout the global economy, integrating satellite intelligence has become a standard requirement for managing physical assets and assessing risk.
Finally, Part 4 brings it all together with automating spatial analysis, leveraging autonomous AI agents for GIS and Streamlit dashboards.
This is the final product of our workflow, a topographical dashboard of Vancouver that integrates live retail traffic with hydrological flood risk models. We are going to build this entire commercial and environmental interface from scratch in 5 minutes, without writing any code. We'll do this by delegating the data processing and software engineering to an autonomous AI coding agent like Claude Code or Gemini. You only need 3 things to start: an empty folder on your desktop, an AI API key, and your raw data files. For decades, these maps required deep proficiency in computational geometry and Python. Today, the barrier to entry has shifted toward the user's ability to articulate geographic logic. To begin, we've placed 2 files in our project directory: a CSV of retail point of interest data, and a GeoTIFF of Vancouver's digital elevation model. These data sets were sourced from decentralized marketplaces like DataRaid, which allow you to find verified geospatial providers using natural language. Open your terminal and instruct the AI to build a virtual Python environment that includes geospatial libraries like GeoPandas and Rasterio. You must also explicitly command the agent to configure the execution path for the Whitebox Tools Rust binary. Because Whitebox Tools is a standalone executable rather than a pure Python package, the agent will fail to run your hydrological models if it doesn't know where the binary is located. Once prompted, the AI takes over, executing the setup commands and populating the workspace with the necessary folders and dependency files. The agent handles the C library dependencies and environment isolation that traditionally required manual troubleshooting. With the environment stable, we provide the master analytical prompt. This tells the AI to clean our data, run the flood models, and merge the two datasets into a single GeoJSON. Structure your prompt by assigning the AI a role, like Senior Spatial Data Scientist, and detailing the exact data schema and file paths. You must also include an instruction to project the vector data to UTM Zone 10N, the accurate local projection for Vancouver. Without precise coordinate instructions, you risk a spatial hallucination called the red bird anomaly, where an AI generates flawless code that is geographically false. If the AI defaults to a web Mercator projection for its math, it will produce a functional-looking dashboard while severely distorting the actual distance and area measurements. Functional code does not guarantee geographic truth. The AI requires human structural guidance to ensure mathematical accuracy. Even with a good prompt, workflows can halt. Here, the terminal throws a red stack trace identifying a spatial index mismatch. AI agents frequently attempt to hide these errors. They may swallow the exception and insert plausible-looking placeholder data to make the final application appear successful. We prevent this by establishing a fail loud, never fake policy. We command the AI to surface every error rather than substituting fake values. When an error occurs, copy the terminal output and feed it back into the agent. The agent uses chain-of-thought reasoning to decompose the failure, adjust the spatial join parameters, and re-execute the script until it passes validation. In this workflow, debugging becomes a process of managing the agent's logic through iterative feedback rather than scanning for syntax errors. Now that we have our enriched data, we command the AI to build the front-end interface using the Streamlit framework. We tell the AI to use Folium for the base map, overlay the flood risk as a color-ramped heat layer, and configure interactive pop-ups for our retail markers. The agent synthesizes the Python backend logic with HTML front-end rendering to write the complete application file. To launch it, just type streamlit run app.py into your terminal. The AI has translated a multi-step geoprocessing pipeline into a clean web-based interface in seconds. The terminal transitions into a browser window, revealing our finalized dashboard. Clicking any marker reveals the metadata we joined earlier: historical foot traffic, brand affinity, and the calculated flood risk score for that specific site. We can use the sidebar sliders to filter the consumer data in real time, visualizing how foot traffic patterns interact with the terrain. By delegating the execution to AI agents, we moved from raw, disparate files to a multi-layered analytical model and a deployed UI in one session. As technical execution becomes a commodity, the practitioner's value shifts. Success is now defined by your domain expertise and commitment to validating geographic truth.